Hi everyone. So today we are going to discuss this paper, Megabyte, that is predicting million byte sequences with multi-scale transformers. So, like in this paper, what it like introduces is that earlier we are using transformers for these decoding, generating tasks in which we use normal fixed token size or fixed input sequence length, which indirectly gives bad results on data sets which we have to input a large number of sequence lengths, such as, let's say we take an example of a book, or we take an example of very long financial document, or let's take an example of an audio file which will be very large. So for all those things, for all those modalities and all those data points where the input sequences are very large, then some of these transformers which inputs tokens, which uses tokenizers, like performing not are not going to perform very good in those portions. So, like for that particular reason, the authors of this paper introduced this methodology in which they are going to use these byte level modelings instead of making it tokenized, instead of using the tokenizers. So what tokenizers generally does is it's going to divide the particular text input into different tokens, such that, like, let's assume we are using a word flying, so it will tokenize it as fly, and like one token would be fly and another token would be the ing or something. So these can be things, but in byte level modality, what it will do is it will make it, instead of converting into tokens, it will consider the each bytes of these input text, and use these bytes to learn the encodings on its own. So for this, in this particular paper, they introduced this multi-scale end-to-end differentiable modeling, which they claim that it's gonna predict millions bytes easily. So actually, yeah. So this is what I discussed. Key what these difference between tokens and bytes. So for, like, when we are using a large, so tokens will generally use large vocabulary. It will have, let's say we are using we have made a tokenizer for English language. So it will be a very large vocabulary which will be fixed only on English language. So it has learned something which is in that particular language. So it's restricted to that it's restricted to the section on which it was trained on. And so let's say if we give input of some new word, let's the example that's given at the bottom. Let's say there's a new word pond, PWNED. Now not a it's a new word, or it's something misspelled word. So the tokenizer will not understand what it is, and it will tokenize it in this way, such that, like, there will be a classification token, and it will classify that first part PWN to be an unknown token. So now there can be like some set of tokens which was not trained using this tokenizer. Now all of these will be considered as an unknown token. Now there's no difference between all those unknown tokens, and hence the learning of the model can be affected using this. And like there will be a higher compute to incorporate these large input sequences which we will give for tokenizing. So byte level encoding hence does not tokenize these stuff as like PWN. Instead of it, it will take the characters on its own, like such that H, E, and all these things. So, and try to learn the encoding on its own, on this new set of these characters or these bytes. So this will remove this portion. We have to train a tokenizer on a particular set of English set or something else. And since we are going to deal with different modalities also, such as images or audios. So on these particular portions also, byte level encoding will be much more resilient and much more useful as compared to the tokenizer part. And it was also empirically noticed that the byte level encodings are a bit more resistant to noise as compared to these tokenizers. Now we'll straight up go to the model's architecture portion, and I'll talk about this later on. What slight changes can we do to incorporate some other modalities or some things. So first of all, we'll see the model architecture which is in front of you. So this consists of three major portions. First is patch embeddings, second is global models, and third is the local models. So what these patch embeddings do is will give an input token of some input sequence and we'll divide that into different patches. We will fix a patch size and we'll divide that into a different patches, and then we'll loosely concatenate those to like loosely concatenate those embeddings to for each of these bytes of the size patch of this like size of the patch, and then we'll input and then we'll add upon these other factors like positional encoding and all, and then we'll pass this to the global model. So global model is nothing different from a autoregressive transformer, which what it does, it takes an input of a patch representation, uses self attention mechanism and some causal attention masking also, and gives that representation of of the input patches that was given to it. And now when we get these out like representation out of these global models, we transfer them to local models. And now the global model was dealing on patch level, but now these local models will deal on byte level instead of patch levels. And these local models, they'll do is they'll contextualize these patch representation from the global models, and they'll try to auto-aggressively predict the next patch. And like, let's say we'll take an example here. Let's say this local model and the first location, which is predicting byte as an answer. So we'll start with a like padding token, and then it will try to predict this token B in it. So there will be an intra patch prediction also in this patch in this local model. And if we like go a bit more deeper into these equations for it. So let's say we have taken input sequence of like bytes of sequence of x0 to xt. So if we'll consider patch size of p, then we will have total number of k patches of size like t by p. So at the start, what patch embedder will do is it will take these x0, x1 and all, and it will have a lookup table of these embeddings of size dg. So dg is the size of that lookup table of the embeddings. So that those embeddings are learnable parameter, which will be learned later on, which we will learn in this whole process. So what this does is this ex of global embedding. So what it does is it's a kind of a lookup table which will bring that embedding of that particular x0 or x1, and it will add it with its positional encoding, and hence giving the like input for the global models. So if the k is 0, so like for k patches, so for first patch, so this is going to be the first patch, right? So we want to make it auto-regressive. So that's why we give an like padded patch at the start, and we'll remove the last patch for it, and such that the first patch will be like an empty patch. And then after that, we will use these HT embeddings that we received from the earlier portion, like from that equation that I just described. So this will be like input of that global model, and then what that global model will does is it will utilize a self attention network to have this inter patches attention, and it will assign weights and all, and it will update all these parameters, and it will give a new representation for that thing. And now we'll have this edge 0 to k. So this will be an output for k number of patches that we give. So here we had k number of patches, and now what this local model will does is it will take these k patches, and it will like now will separate these patches separately. So what I'm trying to say is for that one patch, there will be p bytes inside that patch because the patch size is p. So now it will separate that thing, and it will try to look upon its previous neighbor, its previous patch to predict the next previous byte to predict the next byte inside a particular patch. So it will be an intra-patch thing. So this will be an output. This HK this portion. This will be an output from the global model. So this is the output that I'm talking about right now. And when p equals to 0, so now we are considering this one, na? So when p equals to 0, p is this number of like which part of this patch we are talking about. So when p equals to 0, so it means that since we are trying to start the autoregressive part, we'll give this padding of 0, and it will add this e patch with this parameter. So what does this local model does is it it will not take our previous global embedding was of size dg, which will be larger as compared to dl, but so will reduce the size of uh, this embedding using this WGL. It might be another like neural network which will reduce the size of it, reduce the dimension of this particular thing to convert the dimension from DG to DL, and we'll add this local padding in it. So, but when we are considering, let's say, the first byte, that is this B, when we are looking over this part, so we'll take this as an example, like k of p plus p minus 1. So let's say that here the k will be 1 and p will be 1 also. So k, the patch size is p. So k into p will take us here, and then p minus 1, small p minus 1 will take us here. So that means you're going to use the encoding of this particular portion to plus the encoding of this global output to predict this b as our output from local model. And then in the next step, we'll use this b output, this b along with this our global models to predict the y. So in this way, we'll try to predict inter-patch predictions like continuously. And so the local model will have another like transformer, autoregressive transformer layer that I was just talking about. And at the end, we'll have a softmax layer which will give us the probability of which word must be chosen as our output. So like this is a whole generative process of this megabyte architecture. So, like what they discussed these improvements that they described, key we are doing these improvements as compared to the vanilla architecture of the transformers. So they say they have introduced subquadratic self-attention, and they have reduced these floating point operations in feed forward layer, and uh, and they have introduced this parallelism in decoding. So if we talk about this parallelism in decoding, so by it's generating for like representation for patches in parallel inside that global model. So they say it will reduce, it will make the model to 40% faster than compared to transformers of size 350 million parameter, and their model will be 1.5 billion parameter. But one thing that they talk about in the whole paper is that they'll try to make the compute to be same, of same budget and same everything, and but their parameter size, the parameters that they're going to be learned, that it's going to be larger as compared to transformers, such that we can incorporate more and more number of parameters in the same compute in the same size as compared to uh, normal transformers. So here only say we can see that their model is 1.5 billion model as compared to transformer, which was only 350 million model. We'll look up in depth for the other two. So let's say we are talking about subquadratic self-attention. So what they say ki they are using the subquadratic self-attention, which means ki they'll reduce the complexity to let's say O of n of 4 by 3, n to the power 4 by 3. So we can like look upon this key how this is happening. So like as a function of sequence length t and a patch size p. So the global model will have a sequence length of k which is equals to t by p. So the attention in it will use like k square operations, which will be like t by p, t by p to the whole square. And for our local models, we'll have k sequences, each of size p. So it's like complexity will be like for attention it will be p square, and then we'll have k sequences. So we will make it k times p by p, k times p square. So it will make it complexity to be pt. So in this way, let's assume we take the since patch size is a parameter that we can control. So we take p to be t to the power 1 by 3. Then the complexity will turn out to be t to the power like 4 by 3, which is subquadratic which is as compared to normal transformer, which is t square. So this is where they are saying they have improved the time usage and the complexity part, and by making it subquadratic. And another efficiency analysis that they said was key use of floating point operations. So they said ki 98% of the floating point operation in normal original transformer are used in used for feed forward layers because they use this positional feed forwarding, uh, positional feed forwarding approach. But instead of that, they said ki they are using this per patch feed forward layer as compared to the normal per position feed forward layer in the original transformer. So let's say that original transformer will have an M non-embedding parameters in the feed forward layer for sequence length of t, which were our input. So it will hence roughly use it's like two is an empirical number. So it will roughly use two empty for floating point operations. But in this megabyte approach that we are discussing right now, megabyte will use like let's say for global model will use mg parameters. So since the global model is of like k sequence length, so it will and for local models it will be like k sequences of p length. So it will use this number of floating point operation, which is 2 into t to the whole m divided by p plus m. So like if we consider mg to be very greater than m, which we can control. So if m is the number of non-embedding parameters for global model is very greater than non-embedding parameters for local model, then this will be this will allow to make us like p times larger models for same floating point operation as compared to the normal transformers. So this is another part where they say they are trying to increase the efficiency of these models. And now we'll talk about these variations. For if we want to include different kind of variations, we can include such as we'll use convolutional patch encoders also at some part when the modality is let's say an image. So if its modality is an image, then we not we will try to make it translation invariance also. Okay, so for that, what they do is they augment this embedders with some 1D convolutional layers, which we can be of size 3 or 5 or something, on increasing number of kernel sizes. So for that, since we'll use these convolutional layers of over it, so instead of just looking at its patch, it will just look a bit more nearer to other sequences, like other bytes also in that sequence, which will make it like understand the local information much better as compared to the original one. And one more variation that they talk about was this cross patch attention, in which instead of looking like the previous number or the previous byte, they'll try to use and the embedding that they got from global model for that particular patch. Instead of looking over that only, they'll use an attention mechanism for this patch also for some, let's say, one or two patches nearby it. But if we are including that, then we are surely going to increase complexity. So that was one other thing. So one more thing that they described was key. There's another approach called strided inference, which they have incorporated at some part key, which can also increase our prediction part, but it will double the inference cost because what it does is it offsets the input sequence by p by 2 position, as you can see in this particular diagram. So it will offset this particular uh, at inference time, it would offset the sequence and it will try to predict the outcome. So they did this because like they observed empirically when they are trying to predict the sequence inside a patch, the starting numbers are getting predicted like at very good accuracy. But as we go at the end of that patch, the log probability was decreasing very much. So they utilize these patches, these started inference, and they use the starting portion of the other this strided inference portion for the starting phase, where the ending phase of the previous one is going on. So in this way, they are like trying to make it much better in inference as compared to the previous one. But since we are using two times, so the inference cost will be doubled. So that was one trade-off that we have to see for that thing. And now, when they talk about this training, as I said earlier, they try to focus more on key they want to make the compute and the data budget to be same as compared to the other models, and they try to showcase that they can incorporate much larger number of parameters for the same compute. So they try to make these all these models in such a way. They try to compare all these models in such a way that these conditions is satisfied. So they implemented these decoder only transformers, and there's another model called Perceiver AR, which was state of an art for these kind of these bytes portions. And since Perceiver AR's like I think code was not publicly available, so they implemented their own using the research paper, and they utilize some of these techniques like fully sharded models or mixed precision training or some optimization techniques, like to get the best result out of it. And they trained this on different modalities, which were like language, image, and audio. For audio, they said that they received the state of an art for as compared to others like Transformers or Perceiver AR, which was like 3.47, and this is like in bits per byte. How many bits it is requiring to predict the new to say what the new token or the next token might the next character or the next to represent a text portion of it. So this is like the all these inferences were done in this bits per byte parameter for it. And we'll look upon the other modalities also. Let's say like language model. So for language model, they use these five data sets, which was PG19, which was English language books, which was before 1919, and these codes, which were like open source available codes available on like some which were like under MIT license or Apache license. And the arXiv one was technical research papers available, and books were also like English language books, and the stories were like the data set which was scraped using it is a subset of scraped data using the famous data set Common Crawl. So like these all data set they train their model on, and they had this control experimental setting for 80 billion bytes, and they as I mentioned they tried to make it same budget as compared to others. And they said so at the end they used this transformer of size 320 million for context length of 1024, and this perceiver AR for this 248 million of context size 8192. And they try to make it same to make the comparison in a better way. So they utilize their global model of size 758 with a local model of size 262. As you can see that the size between these two differ a lot, so hence that mg and ml that we talked earlier will also differ, I mean, in a large way. So they use this thing, and what they said key this bits per byte performance analysis that they did, it was better as compared to the other two models, this transformer and persevere, for all of these data set that they trained it on. But when they when they look for like bigger picture, let's say these word level perplexities. So what these other models, these block recurrent and the other models, compression transformer, they use tokens, not bytes, to make the fair comparison. They transferred their these mechanism from bits per byte to word level perplexities, and then they compared it, and it was found key. See, it was found that they are using less number of GPU hours and they are less using less number of time compute, and their result they say it's a bit like competitive as compared to these block recurrents and other transformer XL, but it wasn't state of the art in that particular portion. But they but they performed better as compared to other byte level models that already exist, such as this perceiver Rayon and transformer. But they were not able to beat these tokenized sentence piece models in this language modeling task. But with this other things comes key, like the other limitations of tokenizers come along with these block recurrent and all these models. So like there's an like hope, and there's a like possibility that we can use these byte level models in our future, as like the results are like competitive, and they are going to incorporate different modalities, and they're going to removes all these shortcomings of these tokenizer models. And like they did this analysis on image modeling also, and for that they use these ImageNet 64 per 64 data set, and they found that their model was almost state of an art, like as same as Perceiver, and they also claim that their model 2.7 billion one utilizes less GPU hours for training, almost half of the amount of the GPU hours to train as compared to the other transformer models or perceiver AI models which already exist, while giving the same bits per byte accuracy level. And they also like try to also try to check their performance on higher resolution. For that they used, like instead of image 64 they used image 256 and image 640, also 640 dataset also. And they said their megabyte model of sequence, they handle sequence length of 1.2 million tokens ECD, but the transformer and perceiver they were having problem in going above this 1024 and 12,000 to context length. And they also said it's received state of the art as compared to the other models for bits per byte evaluation for image modeling part. So apart from these, they also did some other analysis on its parameters. So for that, they use this relative model sizes. So they changed their model sizes and try to notice that how it was differing. So they noticed that for these global sizes, as they increase the global size, uh, so their bits per byte is decreasing. So they noticed that the more better, the more and more parameters of these model size they use, the better the bits per byte value will become. The like less the bits per byte value, the more the better it is. So this is what they inferred from this. And also they use this that strided inference technique that I talked about earlier. And they said when if they use sliding window technique combined with strided inference technique, their bits per byte value is decreasing a lot, but it will again incorporate inference cost to be a bit more. Now they're not only using slided inference, they're also using sliding window technique also, so which will make it 4 times. And for patch size also they try to make some analysis key what changes happens when they increase the patch size. And it's like say like it was observed that there is some patch size in between, let's say 256 or something, which is giving an like optimal result like 3.518 as compared to the very low patch size or very high patch size. So they try to find this optimal patch size for these models. And also they use they try to see which part of their model is an essential part or not. So for that they let's say remove local model portion of it, and they saw that the bits per byte value is rising a lot, like from 0.688 to it rise to 1.26. So and for global model also it rise to like 1.373. So that states key like it is required key the global model and the local model is essential for their portion. And like they also use CNN encoder portion for the other image modality task, which is giving better result as compared to the normal megabyte normal vanilla architecture of their own. So like so these variations that I talked about earlier is working better in some cases such as ImageNet and all. So these were all the different analysis that they did apart from this. So like this was it that I wanted to talk about this megabyte research paper. Thank you.
Hello.
Hello.
So, Weber, like uh,
Huh.
a normal tokenizer, if we use, we will get some kind of numerical representation at the end for each token. So, like, I can't understand how this will help replace a tokenizer uh,
So
think.
So
Yeah.
there will be this global embedding lookup table, right? So there will be an
So
embedding encoding
yeah,
will be
I got
present
that.
inside that. So
So you
let's say there are 256 bits inside an 256 bits. So for each bit there will be an representation inside this embedding, which we can look upon and understand using that portion. So
so
instead of
is
having 32K tokens, we'll have like smaller number of these things. Yes.
but the embedding like with the values of the embedding can be anything, any floating value, right? So but in is it like in this case we only have zero and ones or something like that in this embedding, or
The value inside this embedding lookup table that I was talking about, it can be anything I mean, it can be anything as much as I see. And it's that this dimension also we can vary this DG that I was talking about. Like we can vary this dimension also as per our need.
so is this lookup table similar to uh, the dictionary which the tokenizer uses? Is it somewhat similar?
Yes,
Uh,
yes, it's somewhat similar to that only. Yes.
so then the unknown token problem that you were telling, that will come in this also. That it will not come. I was slightly confused as how this is better than the uh, like, tokenizer that uses a dictionary.
So, like their representation is being learned like on the way only. So let's say this PWN was a new word which it hasn't seen, but right now it will be P or W and N. So the combination will be learned like when the model is being trained only. So let's say instead of PWN it was PYN or something else. So
So
that will be another unknown token.
if it is
So
learned, then that means it must be in the training data, right? If it is learned, it can't
So
be something new.
the embedding of P and W and N, so these will be separately learned, and now they'll try to use this attention network to make the meaning out of it separately as compared to the other one. This is what that they discuss, and they haven't mentioned like in detail about this thing.
It's still not very clear, but okay.
Can we replace the tokenization with this model?
So what this is what they were trying to say ki, in future we might want to replace the tokenizer part using this bytes part, but like they were saying ki, we can incorporate more and more number of parameters as compared to and with the same compute, but they haven't done like they just did the analysis for this comparison key same for same compute we are making the larger number of parameter and the normal transform will have this much parameter and this is our result, but like this there's an empty space key. What if they'll increase more, like let's say they were using 2.7 billion parameters, what if they will use let's say 4 billion parameter, and how much the increase would be there like in their bits per byte performance and all. So that portion that they didn't specify it. So this is like on a like whoever wants to use it, they can like try and train it and see whether what they're claiming is right or not. So like this is one approach that we can utilize and see whether this particular thing is will work or not. But like whether they're claiming ki since the trends are in this way, so it will work.
So what is the output of this model? So let's say we pass in a word. So will it give out embeddings, or will it give out something else?
So so this will give this will give these I think these soft maths probabilities of each words from these patches. So these each patches will give their own output, I think. And I mean, so for the attention portion, this thing will work, right? And at the end, I think there will be softmax probabilities. So this is the like final output. This P, which will utilize the output from these local models, and will give the like probability that this character will be the output. So I don't think it will give encoding. It will give these probabilities as an output.
Okay. So this byte does not relate in any way to the memory bytes, right, which we generally refer the
No,
storage unit. Okay.
no, it does not relate to that. So like it
Okay.
can be like representation of a particular set of a particular, let's say, comma or a dot can be done in less number of bytes also. Like it's not necessary that it will utilize a particular space.
So for audio, it should be very useful.
So they said ki they have received like state of an art in audio modality, and they also said ki for image modality they are also performing very good. But for language tasks, they were not like performing much better as compared to those tokenizer models. But for this audio modality, it was working good.
Yeah, this they mention in their abstract as well. So
Yes. For this
tokenization
image,
free
for
data.
raw audio files and image density tasks, they were performing good.
We're calling bytes is basically characters.
Hello. So bytes can be, this can be considered as character level here also. So these bytes can be such as like white spaces or commas or a letter or something, anything.
So is it like you're breaking each word into some embedding which is present in the lookup table, and then you are using those to pass through some attention layers and then getting some uh, meaningful output, like meaningful embedding for each token. Is it like that?
Yes, yes. They are dividing this input sequence into these like the character bytes, and then making patches for them, and then each byte will have one lookup table represented, just what you said right now. So this, and then using those self attention to make understanding between patches. So patches would be like set of these bytes, which this patches level attention will be done in global models, and for the local model they'll only do this byte level modeling. So they found this, they noticed this key when they're using these word completion tasks. Let's say we are trying to complete this word only WOR, and they're trying to complete it to D. So this isn't that complex task as compared to the whole like sentence completion and all, like big like, let's say they are trying to predict 5 or 10 number of words. So that's why they try to utilize these local models as compared to the global model at the end portion. So instead they might have used two global models also, but that would have given attention of attention of like subquadratic, not subquadratic but quadratic attention only. So to remove and reduce those portion, they utilize that local models at the end, which will take the bytes, which will do the byte level attention part, and the global model will do the patch level attention part.